Okay, page 4 for chapter 4. Let's roll 2 dice, continuing with our statistical experiments. When you roll 2 die, one die has 6 possible outcomes, and the other one has 6 possible outcomes, giving you a total of 36 possible outcomes. And here is a pictorial representation of all the different outcomes. Okay, so what is the probability of rolling a 7? Well, let's see. Where's a 7? Here's a 7. Here's a 7. Here, 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 and here's a 7. Okay. Making sure that I got all of them. So 1, 2, 3, 4, 5, 6 possibilities out of 36 that I got a 7. Notice that the 6, 1, and 1, 6 are both counted, okay, because we're thinking about the dies individually, because this one could be a 6 and this one could be a 1, or this one could be a 1 and this one could be a 6. So that's all counted in there, and reduce that to the probability of 1/6. 1/6 is also 1 divided by 6, which is 0.16 repeating. So if you're told to round it to 4 decimal places, that's going to be a 7 on the end. If you're told to turn it into a percent, that's going to be 16.67% chance that you're going to roll a 7. Okay. This sentence right here is the same as this sentence right here. How about the probability of, let me erase this one. How about the probability of rolling a number greater than 11? Greater than 11 with 2 die. Greater than 10 with 2 die would be an 11. Greater, there's an 11, and there's a 12. So that's 3 out of 36. So that is same as 1/12, or 0.083 repeating. So about 8%, depending on how they want you to round things, or just leave it as a fraction. Okay, this is another way to write the sum of greater than or equal to 10. So that would be 11 and 12. Okay, and then there's 3 ways to get those numbers. Notice that there's only one way when you have a double here. It's a 6 and a 6. There's not anything else to think of like that. There's a 5 and a 6 and a 6 and a 5. So that makes 3 ways. Okay? The sum of 5 or 11. All right, let me go back up here for a second and erase this. All right, sum of 5. How do we get a 5? There's a 5, there's a 5, there's a 5, there's a 5, or an 11. There's an 11, there's an 11. 1, 2, 3, 4, 5, 6 out of 36, which is also 1/6. How about rolling doubles? Rolling doubles, there's a double, double, double. All right, if there's 6 sides, there's 6 different doubles. So 6 over 36, or 1/6. Okay. Well, there are 3 basic interpretations of probabilities: classical, empirical, and subjective. The classical approach requires equally likely outcomes. If the outcomes are not equally likely, we must use observation of what happened and we must rely on our knowledge of the circumstances to make an educated guess. So the classical probabilities, each outcome has this in a sample space is equally likely, one can calculate the probability of an event occurring based on the mathematical probabilities only the things that could happen. So look at this. The probability of an event happening is the number of favorable outcomes over the total. So this is what we've been doing. Flipping a fair coin and landing on a head, the probability is 0.5. You roll a 6-sided die. Total possibilities is 6. Each are equally likely if it's a fair die. It's not a loaded die. It's a fair die, as in there's equal chance it would land on any one of the 6 sides. You get the following probabilities. So what we've been doing is classical probabilities. Okay? There are other kinds of probabilities called subjective probabilities, an educated guess, an opinion, a judgment based on inexact information. It's an estimate, the likelihood of an event. So a doctor may feel a patient has a 90% chance of recovery. Feels like it, okay, given things he knows. Chance of rain tomorrow is 50%. We can only guess that it's 50%. We can make an educated guess, but we're not sure. Okay, chance of the stock market will climb this week. Chances a sports team will win a match. You can make all kinds of educated guesses on elections, who will win the elections, but nobody knows. Okay, they can't say. It's not based on actual mathematical calculation. Okay, but an empirical probability is based on observations obtained from statistical experiments, the relative frequency of an event. Okay, so basically you're going to recognize this by its frequencies. Frequency of an event happening out of the total number. All right, so here's an example. The Right to Health lobby claims that the probability of getting an erroneous medical lab report is 40%, based on a sample of 200 lab reports. 80 were erroneous. So 80 out of 200 were 40% off. Mathematical calculations of what happened. Okay, so it's a little different than possible happenings. So the laws of large numbers said as the sample size increases, the relative probability of an outcome gets closer and closer to theoretical. Or actual probability. The law of large numbers is the reason businesses like health insurance, automobile insurance, and gambling casinos can exist and still make a profit. Okay? They basically crunch the numbers. For example, you've been flipping a coin. You decide to bet on heads, believing it's a 50% chance it will come up heads. Your friend tells you that heads has come up the last 9 times in a row. Does that change your mind about what to bet on the next toss? According to classical probability, the coin has no memory, and it's still a 50-50 shot of landing on the heads, so you don't change your mind. The law of large numbers would imply that since it landed on a lot of heads, eventually it's going to land on a lot of tails, so it evens out to the 50-50 total. You could change your mind. The empirical probability cannot be applied because it's a running experiment that has not been completed yet. Basically, is it really a fair coin? Before the game, you could do an empirical experiment, flipping the coin lots of times, and if you eventually get the same number of heads and tails, you can declare it as fair. All right. Some say a quarter is never fair because the head side is actually heavier than the tail. So based on that, using subjective probability, I would bet it lands on tails, head being the heavier side down, more often if the coin was a quarter. Okay, so different types of probabilities. So let's do some empirical probabilities with frequencies. You have a survey of sample of 1,000 employees at a company and record the ages of each. Find the probability of randomly choosing an employee who is not between 25 and 34. So let's look at our chart here. We have ages into groups, and then we have the frequencies of each of the ages summing to 1,000 at the bottom. it says the probability of the age not being 25 to 34. So there are a couple ways to go with that. Notice that 25 to 34 is one of the groups. So basically you take all of the groups and subtract the ones that are in there, and you'll get 634. So this is the total. This is the ones that are 25 to 34. So that means 634 are not in that age. So the probability is, the empirical probability says put those over 1,000, which is going to be that as a reduced fraction, or this as a decimal, or this as a percentage. 63% of the employees at this company are not between 25 and 34. You could do 100 minus this and give the probability that they are that age. Okay? So, that's not what that asked. Depending on how they want it, that's the answer. Okay? Probability of the age is 25 to 64. 25 to 64. 25 to 64 includes all of these people. So you can add them all up. And get 904. Or you can take all of them and subtract the ones that are not. This one and this one. And still get your 904. So 904 over 1,000 reduces, or well, the decimal is that, or 90% of the people, approximately rounded to the whole number. Percentage is 90% fall in that category. 10% don't fall in that category. Reduced fraction there. Okay. Eye color of students in a class. Probability of selecting a student that has blue eyes. Well, let's see. Right there, out of how many need to be asked. So we add them up, we get 24. The sum of the frequencies is 24. So that means this is blue over total, which is the same as probability of blue is 5 over 24, which is about 20.83%, however you need to put it. Okay. Not having brown or black eyes. Couple ways to go for that. You could take the total and subtract anybody who, you could subtract the brown and the black. That's going to give you 9. Or you can say blue is 5, green is 3, hazel is 1, that's 9. Either way, that's the answer. Okay, so relative frequencies are probabilities. Okay, it's important to know what probability statements mean and how to determine probabilities of events, because probability is the language of inferential statistics when we talk about something that happens after we've learned some things. We're going to infer some things about the population, and we're going to use probability, probably subjective probability, right? It can be said that probability is the medium through which statistical work is done. The technique of using relative frequency in an event as a probability of that event is a common way of assigning probabilities and will be used a great deal in other chapters. All right, last. This is classical probability. again, back to the cards. This is a nice layout of all the deck of cards. People don't play as much cards as they used to, so here's a nice picture of them. These are all about the decks of cards, the most important being there are 52 different ones. Okay? Blacks, reds, half the cards are black, half the cards are red. A quarter of the cards are different suits. And the cards have face cards and so forth. Okay, so the probability of selecting a card from a standard deck, one card, that is not an 8. Well, it's easier to find the probability that it is an 8. So 8, 8, 8, 8. So there are 4 out of 52. Okay. So the probability of not an 8 is 1 minus 4 over 52. If you want to do it by hand, 52 over 52 minus 4 over 52 is 48 over 52, which reduces to 12 13s. Okay. You could reduce that to 13s over here. That's 1 13. So if the probability of getting an 8 is 1 out of 13, the probability of not getting an 8 is 12 out of 13, right? So many more can be made, questions that can be asked and answered about cards. Getting an ace is the same probability of getting an 8. Not getting an ace is the same probability of not getting an 8. The probability of a red card, the probability of getting a red ace, that kind of thing. There's a lot of ones you could make up about that. Okay?